Okay, let's get started. So welcome to our first annual Kamiak training event. My name is Aurora Clark, and I'm the director of the Center of Institutional Research Computing. I have with me here today Jeff White, who is our Linux admin for Kamiak, Tim Newman, who's our program coordinator, and then Shenting Sui, who is our computational scientist that helps with software installation. And so today, I'm really happy that we're able to do this. This is the first time we've had a training event. We ran one session this morning, and this is our second session for today. We're going to be following up this training event with a more advanced training event later on in the semester, and so you guys will get like a Qualtrics kind of evaluating this training session, but then also asking for ideas about topics that you guys would find useful for a subsequent advanced training. And so I'm going to begin today, we're kind of trading off on different topics, but I'm going to begin today by giving you an overview of the landscape of Kamiak. We have a really broad set of people that have signed up for this training event. And so there's going to be some stuff that's probably going to be really basic for some of you, other stuff that might be a little bit more advanced, but we're trying to kind of level the playing field within this training session. And so I wanted to give you an overview first of what Kamiak is. And so as a high-performance computing cluster, Kamiak has two login nodes, and we'll talk about how you log in a few minutes, that you access from your user interface, which is your guys' laptops right now. Underneath those two login nodes are a series of compute nodes that belong both as resources to individual colleges, which I'll talk about, as well as individual PIs and investors. And then commensurate with the compute nodes, we also have storage capabilities for people that have large amounts of data storage needs. And so we're going to systematically kind of go through this so that you can understand the overall layout. Now, it is important to kind of to pay attention to where this infrastructure came from. And so this Kamiak is meant to be a follow-on or a latest edition relative to the legacy HPC, which some of you may have used. Kamiak came from a $3 million foundational investment from several colleges, including Connors, Cass, and VCEA, as well as investments from the Office of Research, ITS, and the Provost and President. And so this initial investment paid for a lot of the fundamental infrastructure associated with hardware for Kamiak, so the chassis, the cabling, all this kind of stuff, as well as two staff members that currently help support Kamiak as a user facility. And so sustainable ongoing support is being provided for Kamiak as it grows through investment from faculty PIs that purchase nodes within Kamiak. So to give you an idea, Kamiak, kind of the timeline, the initial cluster and all of the computer components were purchased in the fall of 2015, with the cluster being started to be stood up by February of 2015 or 2016. And then we entered what was called the beta testing phase, where there were some initial users that were putting software on and testing different aspects of the cluster. And then the cluster itself became open to all of WSU-wide, we call it production mode, in November of last year. And so you can see here that we've really had a huge increase in the number of users and the number of investors over time. So what I'm showing here are the number of users' accounts. And you can see that here we're actually at almost about 200 users. In fact, with the amount of users we've had through this training thing, I think we might be over 200 now, so that's really exciting. These users come from all over the university. And so we have a predominance of users in Cass and Connors and VCA, but we have a growing number of users in what I would kind of consider non-traditional high-performance computing units, which is really exciting. So we have people from communications and education and medicine and vet med, and I really think this is important because Kamiak as a facility and a kind of research driver, there are a lot of opportunities for people in perhaps non-traditional units to incorporate high-performance computing into their research. So what we've got here now is a kind of a description of the amount of resources and how those resources changed. And so the initial colleges purchased a series of nodes, and we'll talk about that in a minute. But then basically we have all this infrastructure for which PIs can then purchase computational or computer nodes. And you can see that this also has been growing over time, and we're at right around 100 nodes right now. Now, one thing that you'll see and we'll be talking about is this concept of what's called a backfill queue. And so Kamiak is designed as what's called a condominium cluster, where people each buy in, so investors buy computational resources, they buy nodes, but then when aren't being used, the rest of the university, the rest of the users, they can use those nodes as well. And this is called the backfill. So you can scavenge unused resources at any point in time. And you can see that this is kind of the percent utilization of that backfill queue and those resources. And you can see that's been growing significantly as well. And so in the context of kind of a user facility, this is definitely starting to be something that is impacting the entire university, and a lot of people are really starting to leverage its capabilities. So those nodes that I was talking about came from the foundational investments of CAS, Connors, and VCA. And so CAS has 12 compute nodes. Those nodes are grouped into something called a partition, which is the queue that CAS can use. Connors has 11 nodes. VCA has 3 nodes. And so when we talk about submitting jobs and partitions and things like this, Jeff White will have a whole section in there about how to use those nodes explicitly. The Office of Research has 4 nodes, including nodes, some of which graphical processing units. So for those of you that are interested in lots of speed up and scalability associated with GPUs, you can test those software programs on the OR nodes. And then we're right around 76 to 80 investor nodes at this point. Going along with those nodes, we have memory. And because of the initial investment from the colleges, every user automatically in their home directory gets 10 gigabytes of memory. And you can check the quota that you have, the amount of memory you've used associated with your home directory using this command here. There is extra storage, however, that can be purchased or used within the colleges that goes into a separate folder called /data/ whatever your PI name is. And so this extra storage comes in, like I said, 2 forms. One is through a service center that was set up for the Center for Institutional Research Computing and ITS, where we purchased 144 terabytes total of memory, and about 63 terabytes of that have been purchased by faculty investors. And you'll see at the end of this tutorial how much that costs and kind of ways in which you can become an investor or advocate that your PIs, your faculty research advisors, become investors. But there's also 5 years of storage that was purchased by the colleges. And so colleges within the IT leads of those colleges, so this would be like Wade Lafferty in CAS or John Yates in VCA or Kimmy Lucas or Bill Bonner in Connors, they've each purchased, those colleges have purchased large chunks of memory, and you can request storage from your colleges as well. And so the way in which they do that is up to the colleges, and so to contact those IT leads. But Connors has 200 terabytes, CAS has got 100 terabytes, VCA has 25, and OR has 13. So if we want to kind of go over from an introductory perspective, those of you that may not be familiar with high-performance research computing, an example workflow for someone that might want to use Kamiak would be you logging into one of those 2 login nodes, creating files, moving data off of your local computer onto Kamiak, and then loading a series of software modules, figuring out the resources that you need to use in order to effectively run that software. So if you're going to do some kind of calculation, and then submitting it to the queue, which means submitting it to do a calculation amongst the nodes. This training event is meant to kind of capture this initial component of this workflow. Now, we're going to be setting up and soliciting information from you for an advanced training session, which could focus on a wide variety of things. One of the things it could focus on is kind of more of a post-processing, after you've done a calculation, how can you analyze your data? How could you write scripts, for example, that might optimize efficiency in your analysis, or even things like parallelization of software that you're using, things like this. But this is kind of more on the advanced user end in the context of pre-processing or post-processing or analyzing that data or going for more high throughput research kind of aspects. So our focus is on this end. We're going to try and incorporate perhaps some aspects of this end in an advanced training event later on at the end of the semester. So what you're going to learn today is basically how to navigate Kamiak using Linux commands. And so some of you guys are very proficient in Linux commands and some of you are not, so we're going to do a brief review. how to transfer files on and off of Kamiak, how to find and load software modules, how to submit jobs and perhaps optimize your computational efficiency by considering how the way the queue works. Some best practices associated with being a good user, tips and tricks to installing your own software on Kamiak, how to get help, and also how to invest. So I'm going to begin, and again, parts of this are going to be really basic, so just bear with me if you find it a little basic, but we've got a really broad group of people here. So if you are new to high-performance computing, one of the first things you need to consider is actually how you connect to Kamiak. And so if you're on a PC or a Mac, basically what you're going to be using is a piece of software that's called an X terminal that mimics the command line environment of a Linux or Unix operating system. And so this command line environment is essentially pretty non-graphical, so it's very different from your typical Windows machine. There's a number of free software programs that you can download to allow you to connect to Kamiak. PuTTY is a really great one for Windows. Mac actually has pre-installed software which is just called Terminal, and so this is an example of this X terminal environment. Now, the way in which you typically log on is using Secure Shell Protocol, or SSH. And so here you can see that I'm in my X terminal. I'm SSHing onto Kamiak. You'll notice that sometimes when people SSH, they'll have an additional command flag called -y. That -y allows X11 forwarding, which allows graphical interfaces to be sent through the X terminal and onto your desktop. So if you've got a graphical interface, you would use the -y in there so it could port through that software. So kind of as an overview of Linux commands, we kind of bin Linux commands into several different types. And I'm going to really encourage a lot of you, for those of you that aren't feeling very proficient in Linux, to really go through. There's a huge array of online tutorials available for people with Linux, because Linux is such a broadly used operating system. But I'm just going to kind of go through some of the essential kind of aspects of that now. And so one of the bins that we can talk about, oh, and also this material was sent in that chapter 2 of the tutorial that you guys got sent over your email when you signed up. So one kind of series or types of commands are associated with files. So listing files with the ls command, figuring out where you are in your current directory using the present working directory command, making directories, removing files, copying files using cp, moving files. And then there's more commands where you can actually look at parts of a file without physically opening it up in a text editor using the head command or the tail command or more. There are also Linux commands associated with traversing directories. And so a lot of it is like the cd command, which stands for changing directories. And so being able to navigate the directory tree and kind of thinking about the directory tree as being kind of in a visual way where you're navigating and going up directories and down directories to access different folders. Now, like I said, there's many, many tutorials online, so please, if you don't feel comfortable with Linux, you should really work through those in practice. Really practicing is kind of the best way to feel proficient in this. Now, after you kind of gain some proficiency in Linux, another key aspect is the text editor that you use. And so those of you that are familiar with PCs, you use, for example, Word. Word is a graphical text editor. And so in Linux operating systems, people typically don't use to that extent of a graphical text editor. And so here's a list of some common text editors that are used. Most people use VI or Vim. It provides, it's a really simple text editing software program. It has lots of really useful shortcuts that allows you to do all sorts of really useful things with respect to creating files and moving bits of text around in files. One that's, Vim is, I would say, largely non-graphical. It's really very simple. Those that are more graphical might include something like Emacs. And so within each of these text editing software programs, there are also, again, lots and lots of tutorials online that can allow you to gain expertise. And so we're not going to go over these text editors, but if you're not really familiar with one, it's important for you to choose and practice. So kind of moving along and starting to delve into some more detailed kind of things, less general things. Obviously, if you can log on to Kamiak and do some rudimentary Linux commands and you can open files, being able to move data is really essential. A lot of you guys have data that's located on your home computers or your local computers that you want to move on to Kamiak, or moving that data off of Kamiak after you've done a calculation. And while some people are familiar with some file transfer techniques, there's also more advanced can be really useful to you, depending on how much data you actually need to transfer. And so there's really kind of two ways to think about this. There's transferring data, which is just copying a file from one place to another place, or from one machine to another machine. There's also synchronizing files, which is a slightly different concept in the sense that you're not only copying, but maybe you don't want to copy. So say you have 5 files on your home computer, you copy those over to Kamiak, you run a calculation, Kamiak updates those files, or some of those files. Maybe you don't want to copy all of that over. Maybe you only want to update the ones that have changed. And so synchronization is also a really useful concept here, particularly if you're dealing with large amounts of data. It can decrease the amount of bandwidth that you use and make that data transfer process much faster. So within the transfer-only category, there are things that people typically use like SCP, secure copy, or SFTP, secure file transfer protocols. But if you're interested in transferring and synchronization, then we really recommend the use of rsync, which basically establishes 2 copies, but then once it establishes those copies between 2 different machines, it then does updating or synchronization. So if you have, 10,000 files, it's only going to transfer the ones that have been changed so that you don't use a huge amount of bandwidth and unnecessarily transfer data that you don't need to. This is also really versatile for things like data backups. So if, for example, you want to do a calculation on Kamiak and you want that data to be backed up onto a local machine, you can automate that process, which is really useful. And so some common options, we're going to go through rsync. And right now, we're not in the stage, we decided to design this training session as having an interactive component where you guys log on to Kamiak and do stuff. We're not at that stage yet, so this is just me showing you some examples and things to consider. But we're going to be going through, later on, explicit examples where you're going to log on to Kamiak and you're going to do stuff. So in this case, with respect to rsync, there's some common options that are used often with the rsync command. Verbose is a really common one. Other one is doing this recursively. So it goes down into subdirectories of directories that you may have. Working in archive mode can be really useful because it also does it recursively, but it preserves things like symbolic links and permissions. You can compress the data at the same time that you're transferring it with the -z command. And then you can also, rsync is really big into kind of showing you the speed up associated with the fact that it was able to copy just what was needed, and then it'll pop out to you things like how quick it was for you. So here's an example of using rsync where we're copying data from a local computer to the home directory on Kamiak. And here we're going to first do a copying a file versus copying a directory. And so this is a screen capture of my desktop, my Mac desktop, and I'm copying a file from my present working directory, which is test.xyz, onto my home directory of Kamiak, which is denoted by this /. And so I have the AVZ flags after rsync, which means archive, verbose, and compress. And so you can see this says, do the rsync and move this onto here. It asks me for my password because I'm actually logging in to Kamiak during this process. It builds what's called the file list, which is how it knows what changes may need to be done with files that have or have not changed if I had to do this again. And then it'll tell you how many bytes it took and what the speed up was. So this is really simple. Now it gets a little complicated, or there's just thought that needs to be taken if you want to copy directories. You can use rsync with directories. And so here I'm trying to use rsync to copy and synchronize a directory called codes and scripts off of my present working directory onto my home directory on Kamiak. And you'll notice that I put a trailing slash after this directory. And whether or not you have a trailing slash actually means something and changes the way that rsync actually works. And so with a trailing slash, what that will do is it will only copy the contents of that directory. So let's say I have 10 files in this directory, codes and scripts. rsync will copy and synchronize those 10 files, but it will not put them into a directory called codes and scripts. It just takes the files that are underneath and does that. If I don't use the backslash, then it will copy both the directory name and the files that are underneath it. And so it will create a new directory called codes and scripts that is synchronized relative to my source directory. This is actually kind of important. Say you were synchronizing 10,000 files and you accidentally put the slash in there, you would get 10,000 files right there, and it could kind of make a mess of your working environment. So you'll notice the order of the operations with respect to rsync. It's, rsync, flags, source directory, ending directory of where you want it to be. And so before I was transferring files in a directory from my present working, which was on my desktop, onto Kamiak, and now I'm doing the reverse. So now you can see that my directory that I'm moving, my current file and location, is on Kamiak, and I'm putting it in my present working directory, which is just denoted by this dot. I could also put the explicit path like /users Clark desktop or something like that for my computer that I'm on. And so, so this is just showing you the order of operations that you can go both ways. Now, obviously, when you're considering moving data on and off Kamiak, it might be relevant to you that you only have 10 gigabytes in home. And if you want to move more than 10 gigabytes of data, but you only need it there for a short period of time, you need to be able to consider what to do with that. And so if you do need more space for a short period, we recommend using Scratch. And so we're going to show you right now how to create a workspace in Scratch. So bear in mind, remember, we have all this memory that's associated with this NetApp storage device. And so Scratch is really a shared space within this NetApp storage device that everyone has access to, not connected to a specific node. So this is just a screenshot from our HPC FAQ page. But you can see that basically the way in which we decide to allocate Scratch is using a command called make workspace. So make workspace, basically, it creates a Scratch directory for you. It's associated with your user ID name or your WSU network ID. So here I am logged in. I've got my login is my WSU ID credentials. I'm logged into one of the login nodes, and I type make workspace. This make workspace application creates a workspace for you in Scratch using your user ID, and it has a timestamp associated with this. Now, this is actually really important because your Scratch directories are only meant to exist for about 7 days, and then they get deleted after that 7-day time period. And so this is meant to be temporary space only for you. And so by default, this is creating a workspace for you in Scratch on the shared NetApp storage device. It's running over a 10 gigabyte network, so it's really fast. If you have nodes that are doing calculations and they need access to that data, that's really good. And again, because of the timestamp, it will delete that data after a 7-day period. Now, it may be that you're worried, for example, about the latency associated with that 10 gigabyte connectivity between the NetApp storage device, or you have some other reason. You can actually create Scratch space on the SSDs of the nodes themselves. This is going to be using an application called iDev that Jeff is going to be talking about later. But basically, it will create a space for you on that node. And this will, I have in here that it only allocates a 2-hour lifespan, but that's actually wrong. It lasts 7 days as well. So if for some reason that latency or there's a very specific need to have Scratch space on a node that you're running a calculation on, you can also do that. Now, obviously, if you're using Kamiak a lot, you may end up creating lots of workspaces. And so you can list all of those. And they'll tell you when they're going to expire, when that 7-day period is, by using the ls workspace command, and it'll list them out. And so then you could know, say you're running 10 different jobs and have moved 10 different pieces of data over, you'll know when they're going to expire. So now you should be able, or at least be familiar with, logging onto Kamiak, deciding and thinking about what text editor you want to use, basic Linux commands that allow you to kind of navigate through the system, moving files on and off Kamiak. And so next we want to explore the available software that's on Kamiak itself. And so Shenting, our computational scientist, is now going to take this part over.
I know everybody probably uses some kind of software modules. Here's just some simple command how to load and see what module you have, and some special cases. And if you were logged on to Kamiak, I would like you to just try this command. All those line lists start with a $. The command you can use, so you can try it. So.
And here, I'm actually going to log on to Kamiak right now so that you can kind of see the output for those of you that are not logged on to Kamiak. So you can see here, right when you log on, it tells you to use Module Spider to be able to show all of the modules that are available. And you can see that you get a really long list of all of the available nodes.
Yeah, if you type module avail.
Mm-hmm. So now we can try module avail. And now you get this much nicer list. Huh? The $sign is the prompt. Yeah, thank you for bringing that up. So depending on what environmental variables you've got set up in your, when you log in, sometimes you'll see a $sign, sometimes you'll see a hashtag, but that's just the prompt there.
So the next command is module what it is. And I have a particular module there called lib_int/1.1.4, and that will tell you what that module does. And the next line is module spider. You can you just type module spiders, give you long lists with very detailed information of every module. So you just type module spider and a particular module name, whatever you want to choose. It will give you detailed information about the particular module. So, instead of a long list. So I will go through this list in a relative slow speed. You can follow up. You can just type in. If don't, you cannot type fast enough. You can go back later on. You can try that later on when you go home. So the next one is module swap. So suppose you have a module that a module called m_o loaded, and then you want another module instead of that old one. So you can use the module swap to swap out this old one and swap in this new module. Module purge is basically remove all the modules you have loaded. So it's clean up everything. Yes?
Just one note about module swap. One really useful thing that can be used for on Kamiak is we have basically two sets of modules to use. One's based on the Intel compiler, the Intel Parallel Studio. One's based on GCC. When you log into Kamiak, you get the Intel module by default. If you do module swap Intel GCC, it'll move over everything from Intel to GCC for you. Just as an example of one thing you can do with it.
You mean move from Intel to GCC,
yes.
right?
Yes.
It's actually, you do that, you might as well try that. So you want to look for open MPI, for example. So when the default, you cannot see it.
Correct.
So if you you can actually just, instead of swap, you can just module load GCC. You can type in that right now. And you can do that, and you'll be able to see open MPI and some more things that you cannot see by default under in Intel compiler. So the next thing is module unload, module name, whatever name you want to give it. And the next thing is module load netcdf/4. And I want you to try that one. See what you got.
Why are these just not available? Not installed all the time.
Well, the reason they're not all available all at the same time is because the packages conflict with one another. For example, if you can see OpenBlast on there, has 3 different versions of software OpenBlast installed. So there was one reason that we have modules in the first place, is that we can have multiple versions of the same software installed in Kamiak. You can select which one of those versions of software you want. The other one would be a number of the modules are, well, not a number of them, but some of them are incompatible with one another. So it's kind of impossible for us to always put them all onto the system so they're just available to you. You kind of have to choose which modules you want to use, which software you want to use. If you're also asking why module avail doesn't always show anything, that's another issue. That module avail shows you what's available to you. So if something's based on GCC and you've loaded Intel, it's not going to show you what's available only under GCC. But if you use module spider, that's what module spider does, look at the entire system, every module, everywhere, regardless of what you have currently loaded.
Okay, if you just did that module load netcdf/4, it will come out with this message say L mode has detected the following error, cannot load module, and so on. And it says without load these modules, HDF5/1.8.16. And that's the intentional, right, by design. So it's behind the scene, we put in something that says it requires you load this FDF5/1.518 first, then you load that netcdf4. And you might as well try that now, see if you module load netcd4 now after you load that SDF slash something. Yeah, in particular for Anaconda 3, it's in conflict with Python 3 also, because you could use Python 3 or you could use the Python 3 within Anaconda, because Anaconda has a lot of stuff in there. So you could use a version of Python 3 within Anaconda, or you can use the Python 3 by itself. Yeah. So there's a reason it's in conflict, because you already have Anaconda has one version in it already. So.
Yeah, there's plenty of software that's available outside of modules. Like if you just log into Kamiak, like various commands are there, all the common stuff's there, ls, cd, that sort of stuff. There's plenty of other things available to you. So essentially the idea is common utilities are just available to you and they're there. Anything that's going to be specific to any sort of scientific work is going to be inside of a module.
So then I think finishing out this slide.
Yeah, track module, you load it, you can, what is that? That's the module list. And after you loaded one particular module, and you want to check whether the whole idea of load a module load is load a software a package. Software package has the command, has the library, has the header file, and so if you have in mind, for example, you module load Octave, okay? Then you want to see whether that octave command is in your path after you loaded the module. Then the command you use to check that is which octave. So if you loaded that module successfully, and you did module list and see it's loaded, and you type which octave, you will see that where that it gives you complete path where that octave command is located. And you also can do this env pipe $LD underscore library underscore path, and that will give you the path of the library for the module that you just loaded.
So one thing that I think is important to note about that is all this module is doing is it's modifying your environmental settings within your bash profile file that all of us have, right? So everyone, because when you log on and an account is created for you, you're working within what's called the bash cell that sets all of your environmental variables. And within that is a file called your bash profile that has all sorts of things that are put in there by default. And so you can manually modify your bash profile file to have all of these parameters in there already. If you don't want to load a module every time you log in, you can just manually stick it in there and it stays there. But if you want to use module load, it puts it into that bash profile file. And if you use module unload, it takes it off again, basically. Those environmental variables derive from when your bash profile runs, and then you can add basically that to in the session that you're in. And then it's there all the time.
What you just said contradicted to some contradictory. So just to clarify, when you run the module, it sets up your bash file and then that bash, or your profile. So that'll be permanent then? So the
No. So you're right. That was a little confusing. So you can manually, so you have a bash profile file and it has all of these things put inside of it. And every time you log in, it runs that file and sets all of those environmental variables, right? So if you put in something permanently into your bash profile file, like this environmental, you could do in fact, I think later on it's not setenv, what is it in bash? Export yes, it's an export command. I use CSHRC, not bash, but in either case, you can permanently put it into your bash profile file using the export command, and it'll always be there. What module does is it temporarily loads that environmental variable into the session that you're logged onto. So it's not a permanent thing. Yeah, I thought it actually, if you opened it up, it didn't, but it just does it. It's like if you typed it in on a command prompt, because you could also you could type in that command on your command prompt, the export whatever file to add to your environmental variables, and it's temporarily doing that for the session that you are logged in on.
So when you do a module load thing, really the only thing it's actually doing is saying export path equals thing, export LD underscore library path equals thing.
Yeah.
That's all that's happening.
Which you could type in yourself. Yeah, it's just an easier way to do it.
Yeah, it has some other hooks in there to work with other modules.
Sure.
Like earlier, I told you I need this other module to load this module you asked for. So there's sort of hooks to help figure out this big mass of software and how to use it.
So
Basically,
does
yes.
the application have a module definition that does all the linking, or do you guys have to?
We do that with every single piece of software that we put on the system, we have to do that. Basically, when we put software onto the system, there's a little thing that we'll show you on compiling software later that's separate from modules. That essentially we do the compiling of the software. We tell it, install to this shared location under opt apps.
With all the dependencies and everything.
All dependencies get built into that. And then we have to manually write a module file that actually says, okay, variable path, add the path to the new binaries. LD library path, add the path to the new libraries, that sort of thing with every single module that we create.
So this is actually one of the reasons why we encourage users, and at the very end of this, we've got a kind of tips and tricks for installing your own software, because if you are interested in software that you're going to use, or maybe only a couple of people are going to use, it's really beneficial for you to compile that yourself. But if it's something broad that lots of people are going to use, then we're happy to create a module for it so that everyone can load it really easily. But it does take quite a bit of, it's a process to go through and make it a module as a package that everyone can use. So I think this goes through a lot of what we just showed. And we already went through some examples of module loading. So now let's get to submitting of the queue, which is what Jeff's going to talk about. Are there any more questions about the software module stuff? Yes?
Yeah, we're talking, so sorry about that, but relevant to that, we were wondering if you have specific, like if we're working in R, specific packages that need installed. Will those be pre-installed with different modules, or would we have permission to go through and install the packages once we're inside a particular version of R that is its own module?
For some software that does take packages like R and Python, for example, you can pip install stuff inside of Python. For anything that's installed inside of a module, end users won't have any access to create anything inside of that, so you won't be able to install any packages yourself, like conda install in Anaconda, for example. If there is anything like that that you would like added to an existing module, then you can always create a service request on our service desk and just let us know, what software you'd like, and we can actually install that for you into the general modules.
When you do Module Spider, do you see all of the things that have been loaded in R?
No, you don't.
No, you don't. Okay.
No. Unfortunately, that's all those sort of things are kind of specific to the individual software. Like, nothing inside of module systems tells you what Python modules are installed. That's a completely separate thing. And same thing with R, same thing with Anaconda. Everybody else does the same sort of stuff.
So if you did load R, you'd be able to see all the modules that were installed with R.
Right, and then, as users, would we have permission to add other ones?
No, you would have to ask.
Each individual package that we're using.
Unfortunately.
Yeah.
Yeah, and there's some other things you can do. I don't know R specifically, but with Python, you can use virtual environments and things like that to install your own modules in your own spaces in addition to what's available on the system. I don't know if R specifically has that available, but it might be something else that could work for you. So you don't always have to rely on us to install something for you. But again, even if something's available as a module, like nothing prevents you from compiling your own version of it that you can do whatever you'd like with as well. We've had a couple users I've known that have done that as well. That if they can't really use our generic version that's available to the whole system, that they'll make a special version just for themselves that has whatever compiler flag they want or something like that.
Just remember that you have 10 gigabytes in your home directory. So.
All right, so let's go on to the next page. So I'm going to go a little quick on this. If I do have any questions, just raise your hand or stop me or yell at me or do something. Just don't throw things at me. So a little bit on what we're getting into now is you kind of learned a little bit about some of the things that are available inside of Kamiak as far as software goes. So what we're going to go to now is how to actually run something on Kamiak, look at the nodes and resources, CPUs, GPUs, that sort of thing. So Kamiak is primarily a batch processing system that has nodes that are assigned to queues or partitions. If you've worked with Torque or PBS or anything like that that talks about queues, a partition is the same thing. Inside of Kamiak, we use Slurm as the software to manage all of our compute nodes, and that's who actually runs your jobs. When you submit a job to do some sort of calculation, what you're doing is you have a script, a shell script, that you're then submitting into Slurm. That script contains directives for how you want to run that program, how many CPUs do you need, how much memory do you need, that sort of thing, as well as directives for how to actually run your program. You give that to Slurm. Slurm goes and tries to find idle resources to go run that, and it goes and runs your program. For any of the nodes that are inside any of these queues or partitions, we have CPU cores, memory, as well as accelerators such as GPUs and Xeon Phi coprocessors. Inside of Kamiak, unlike a lot of other clusters, especially older ones, Kamiak does not allocate entire nodes. You don't say, I want a node. You say, I want 10 CPUs and X amount of memory, or I want a GPU and 5 CPUs, something like that. And Slurm by itself doesn't perform any sort of magic. It's not going to take your program and just make it work on a cluster or anything like that. It just runs your program. That's really all it does, and sets up a little environment for you that gives you the resources that you've asked for. Okay? So if you haven't logged into Kamiak yet, this is a part where if you'd like to, you can follow along. As Roar mentioned earlier, I always have it SSH-Y. If I'm on a machine, I don't already have that config loaded in automatically, so I can do X11 forwarding, but we won't be using that today if you haven't bothered to do that. So Slurm is software that we didn't invent. It was made by a company that's now known as SkedMD. So the commands I'm showing you now are a very small subset of what's really available inside of Slurm. For the full documentation, go look at SkedMD's website, which we'll have a link for at the end of this presentation. That's going to have the full information on what Slurm can really do. This is just some common things you can do with it. So to start off with, we'll look at sinfo and sq. And notice most of these commands start with S for Slurm to show you what's available on the cluster and then what the cluster is doing right now. So rather than just reading this, let's switch over to the actual cluster and look at it. Although I am going to become myself because I like to. Instead of being Aurora. Okay, so if we do an sinfo, slurm info, tell me what is going on inside this machine. I'm going to pipe it to less just so I can see everything that's going on. This is every node and every partition that is inside of Kamiak. On the left is the partitions, which again is the same thing as a queue, just different word for it. The maximum time limit you can use that queue for any particular job, which if you don't specify time limit in your jobs, by default, you get the maximum time limit. Then information about what nodes are in there and what the current state of those nodes happen to be. A lot of the stuff on the right, not all that important to know what it is or look at it. But if you want to see what's on the cluster, what is it doing, what partitions are there, sinfo is how you determine that. Take a look at sq real quick. Again, pipe it to less. And this is everything that's in the queue right now. The queue is going to include all jobs which are running, pending, or held. It will not include any jobs which have been canceled. It will not include any jobs which have completed, either successfully or due to an error. So if you run a job or you launch a job and you go and look in SQ and you don't see it anywhere, well, that's because it's dead. It either finished successfully or it finished unsuccessfully, but it's not there anymore. There is no more job. That's why you can see in here we have a few that are completing, a few that are pending. That's what the PD means. It's also a -long option to not have so many acronyms. And then plenty of jobs that are running right now, which is what all of these R's mean. You can see we even have users that are using multiple nodes within single jobs, which I'll show you how to do in just a moment. Okay. One other command I'll show you real quick is scontrol. Most people don't use this one a lot, but if you want to know real detailed information about something, this is how you figure it out. So if you have access to, say, a Beckman partition and you see what nodes are inside of there, you want to know, okay, well, what's inside those nodes? What can I use inside of there? You can get the node name and just say, okay, scontrol, show me what's inside there. In this one, we can see for this node, SN11, special node 11, he has a Haswell processor, 24 cores, 8 Tesla GPUs, this amount of memory, and these other things that's talked about down here that we won't worry about. This is just an example to show you how you can get information about what's available on the cluster, what you can really do with it. Then sbatch and srun are how you actually run a program on the cluster, and we'll show that in just a moment. Okay, just options of SQ, sinfo. Now, at the bottom of this list in sinfo, disregard the test one, there's this special little Kamiak one. The Kamiak partition is what we call the backfill partition. The backfill partition contains all nodes inside of the cluster, regardless of who owns them. So we have basically 3 sets of types of partitions. Sponsor partitions, Connors, Kaz, VCEA. Investor partitions, Clark, people who've bought nodes for themselves. And then the backfill partition. If you use the backfill partition, you have access to all of the resources on the cluster as long as they're not being used by anyone else, and particularly if they're not being used by an investor. So right now, Aurora's not using all of her nodes right now. So if I wanted to, I can submit a job into the Kamiak queue, this backfill queue, and my job may run on her resources. So if we walk through what would happen in that case, say I, as a unprivileged user, I don't own any resources, so I just submit my job into the backfill queue, Kamiak. Slurm looks through, tries to find where it can run it, and he happens to pick CN83 as the compute node to run my job on. CN83 is also a member of the Clark partition. At that point, my job would be running. Everything seems fine. It's great. But if one of Aurora's users, one of her lab students, then has their own job, they submit that not to the backfill partition, but to the Clark partition, which both of them have the same node in it. Slurm will again try to find idle resources. If it can't do so, it will kill my job, because I'm a lower priority backfill user, and run that student's job instead. And then my job, my little backfill job, will be canceled, completely killed, and then resubmitted back into the end of the backfill queue. So the backfill queue is nice that it gives you lots of resources that you didn't have to pay for. You didn't have to get funding or figure out anything for that. You just have access to it. But investors have priority access to the nodes that they own. So if your job happens to get preempted by someone else who owns the node, that's fine. It'll go ahead and just resubmit it back to the back of the queue to try again on some other free resource when it has time to do so. If your workflow does not allow your job to be restarted, say you're doing checkpointing or something like that, where every time you submit your job, you have to fiddle with it a little bit to tell it exactly what to do. You can also tell Slurm, you can give it an option in your job to say, my job is not resubmittable. If I happen to be killed for any reason, don't resubmit me. Just send me a message, say something went wrong, then I'll go submit it manually. But if you can resubmit automatically, then just let your job continue getting killed and resubmitted until it finally completes. Or make shorter jobs. I don't really have any good statistics to really quote on that to say how much really happens or how many jobs have been preempted. I know they do get preempted. My own jobs have been preempted. I don't own any nodes. I work in the Kamiak partition for the most part. And for the the test jobs I'm talking about now, if you're logged into Kamiak, do an ls on /data/Kamiak/training. There'll be 3 scripts inside of there. Those are the scripts I'm talking about. So I'll take a look at those directories, make sure you can actually see that /data/Kamiak/training. Okay, and inside of that one, if you see a script called test_GPU_job.sh, if you run cat space that program, you can see the first submission script I'm really talking about right now. So then if you just look at one of those, like you cat space one of those file names, essentially what you're going to see in that first one, test_GPU_job.sh, you're going to see that it's going to start out essentially just with a shebang line for bin bash. In this case, it's just basically showing that this is in fact just a shell script, a ye olde shell script that's been around for decades to make this work. Then the next few lines you're going to see there are going to start with a hash and then an all caps sbatch. And what these directives do is they're actually just giving options to the sbatch command itself. So every thing you see after that little hashtag sbatch is a -- option. That's the same option that you can actually give on the command line directly to sbatch rather than putting it into the file if you wanted to. So the first kind of directive you're going to see in there is I'm asking for the number of tasks and the number of CPUs I want. For tasks and CPUs, you kind of look through Slurm's documentation for some more detailed information on exactly how that works, on what the difference between a task and a CPU is. Remember, everything in Kamiak is allocated by CPU core. We don't really care about entire CPU themselves. Okay, so the tasks versus CPUs thing, look through SCEDMD's documentation on MPI jobs when we get there to get a little bit more information on what that is. But for this serial job I'm doing now, I'm simply asking for 1 CPU, 1 task. That's it. I want 1 core. I don't want anything more than that for CPUs. The next line in here, I'm saying I want 1 node. In this case, I'm saying I want a minimum of 1, a maximum of 1 node. You don't always need to put that in. It's just a hint to Slurm of exactly what you want. Because if you're not really careful with what options you give Slurm, if you just tell it, I want 20 CPUs, well, it might give you 10 on one node, 10 on another. And if you're not using an MPI program that can handle that, you're going to have a bad time. So in this case, I'm explicitly telling Slurm, give me 1 compute node for all of my resources, even though I'm only asking for single core. I'm also asking for a GPU resource, and I'm only asking for single one of them. And I'm going to submit this to the backfill partition, which is named Kamiak. And then the rest of this program right here is my job. That is my code that I want to run. So I'm just saying, okay, give me a little echo line to tell me what's going on. I'm calling a module. I'm loading a module inside of my program, inside of my job, because I want to use some of the software that's already there. And then inside of that, this CUDA module is a program called Device Query. This is a little program that NVIDIA packages with their software. And we're going to see what happens after I actually submit that with sbatch. You notice here it's important that I said sbatch space my script. I didn't run my script. Don't run your script on the login node, or it'll actually try to do the computation on the login node, and that's not what you want. You want to submit your job into Slurm to do the work. So let's actually take a look at that real quick if we can. So if I do an sbatch, you notice right now I'm in my home directory. That's kind of important. If you're CD'd into that data Kamiak training, CD back into your home directory. Or else, if you're going to do this, or else it will not work. I'll explain why in a moment. So if I do sbatch data Kamiak training test GPU job, there's my job. It just told me it's running. So if I now do scontrol show job, and then that number, 474838, there's everything about my job that Slurm knows about. An important note about this is right now you'll see it as completed, so you won't see it in SQ, just like I said before. You do see it in scontrol show job. However, this will go away very quickly. This expires in like 15, 20 minutes, I think is what I have it currently set to. So it's really something that's more made for looking what your job is doing as it's running. But if your job just completed, this is one way to see, okay, what did it do? But you have to do it kind of quick, because Slurm does not recall this information for very long. It throws away old jobs for resource reasons, basically. So in this one, you can kind of see what it did. I asked it for 1 CPU. It gave me 1 CPU. I asked it for 1 GPU. It gave me 1 GPU down here. You also see that it gave me a certain amount of memory. I didn't ask for a certain amount of memory in my submission script. The way it works on Kamiak is every time you submit a job, if you do not specify how much memory you want, you get an amount of memory that is proportional to the amount of CPUs on the nodes in that cluster. So if you're submitting to a partition that has our standard compute nodes that have 20 CPU cores, if it has 128 gigabytes of memory, if you ask for 1 CPU, you get 1/20th of 128 gigabytes of memory. If you're on a partition that has 250 gigabytes per node, you get 1/20th of 256, for example. In the Kamiak partition, it's kind of the lowest common denominator, so you're getting 128, because that's the lowest amount of memory on any available node in the Kamiak partition. If you do require more, you can always add a --mem equals value to your script, so regardless of how many CPU cores you're using, you can specify exactly how much memory you're using. There's 128 gigabytes per node is the minimum we have inside of Kamiak. Some nodes have 256. We also offer 512, and there's big mems with terabytes of memory. So how much memory you get by default, if you don't specify any, depends on which partition you're submitting to and which nodes are in that partition. And down at the bottom here, you'll see some important information that is the working directory. That is the directory that I submitted it from. So that's what Slurm's going to consider its working directory, just wherever I submitted the job from, wherever I happen to be sitting when I called that sbatch command. And then it's going to show me standard error and standard out. Right now it's using the same file for these. If you want, you can specify your standard error and out to go to different files. Essentially, this is the output of your program. So when you run that, when you give Slurm that one script, you told it to go run something. Well, these output files are how it tells you what happened, what is the output of your program, unless your program's automatically doing that and stashing data wherever you want. So in my case, it's going to be right here in my home directory as slurm-my job ID, because I didn't specify where I wanted to put my data. This is where Slurm picks by default. So I looked at that file. There's the output of the job I just ran a few minutes ago. This is the output of that device query command. And you can see in here, remember that the script, I asked for 1 GPU, I got 1 GPU, and it's a Tesla K80 GPU. So that's a very simple example of just how to run a serial job on Kamiak. Let me just bring that up 1 second real quick. Kamiak training. Okay, so now the second thing I'm going to show you is moving on to MPI jobs. So a serial job is fine if you don't have software that works with MPI or anything else that can do process on multiple nodes at one time, or maybe you're using pthreads or something that could use multiple threads or multiple CPUs on one machine. And that's where this sort of script can come in handy. So let me switch back over here if we can see it a little bit better. Test MPI job, test_MPI_ job. So this one's pretty similar, except I'm asking for 1 CPU per task. I'm asking for 5 tasks per node, and I'm asking for 2 nodes. Okay? So what I'm asking, essentially what I'm telling Slurm to do is give me 5 processors on 2 different nodes, so a total of 10 processors. And again, look through Slurm's documentation for real detailed information on task versus CPU and what you're really trying to do, how to instruct Slurm to do what you're looking for. I'm also including a constraint on here to tell it I want an Ivy Bridge node. If you remember, if I did the S-control show node SN11 earlier, that's how I can learn what type of CPU it has or what constraints I can put on it. You don't necessarily need this for most of the time, but if you're compiled your software to a specific type of node, you can always require that node in your jobs. And down here, I'm specifying where to put my output and error files. This one's saying %j.out, so it's going to put this into my current working directory as the job ID .out. So Slurm automatically translates %j to .out. There's plenty of other little variables like that inside of Slurm, so if you want to do stuff like that, you can look through the documentation to see what else is available for you. Inside of this one, I'm also just saying a few more echo statements, and I'm running, using srun, an MPI program. If you've used MPI run or anything like that on other systems, Kamiak doesn't really support MPI run. You have to switch it over to srun, and the options you might have to give to your program can be slightly different in order to make that work, but it's essentially very, very similar to what MPI run is. And what we're going to do here is now run this one. And again, we're not running the script, we're passing it to sbatch. And I'll do an SQ for myself, -u for user, and there's my job running right now, state R. And it's running on 2 nodes right now, CN1 and 2. And it's done. So, if I now look at 4.7, so on, there's my output file that my program Slurm just created for me. There's the output of my MPI program. You can see in here, it's telling me I ran on CN1 and CN2. These are different ranks I have, and I had a total of 10 processors, just like I asked for. And I ran that program across 2 different nodes. Inside of Kamiak, there is an InfiniBand fabric that's available that's currently connected to every single node inside the cluster. So if you're compiling any MPI programs or anything that's doing any sort of inter-node communication whatsoever, use InfiniBand when you can. You can use SSH or anything else to communicate between nodes, but if you have software that supports libIB verbs, or similar things that can use InfiniBand to do its work, use those. They're much, much, much faster. And now the next thing I'm going to show you real quick is Slurm arrays. So I've basically shown how to run a single core job and then how to run a multi-core job among multiple nodes. In that same MPI one, you can change the number of tasks versus CPUs and number of nodes you're asking for to say you want multiple cores on a single machine. So if you're using OpenMP or pthreads or something like that that can do multiprocessing on a single node, you can start with that MPI example and then just fiddle with the settings you're looking for to tell you that you want everything on a single node rather than multiple nodes. Now for an array job, what these are really useful for is for anybody who is what we call embarrassingly parallel. So a lot of some workloads really only work serially. It's one program feeding off of one input file into one output file. But you can run 10 of those or 20 of those or 1,000 of those at once if you wanted to. That's what we call embarrassingly parallel. It's not in parallel, but you can pretend it is. And that's where Slurm arrays really come in handy. So let's look at that. What I'm doing here is very simply asking for one CPU for each one of my array tasks, and then I'm asking for an array of 0 to 4. If we look down here in my little echo statements, we see some new variables for me, Slurm array job ID and Slurm array task ID. And I'm then creating a little array full of my input files, and then down here I would be calling my program and saying, here, take this input file. What Slurm's going to do at this point is he's going to take this one script and he's going to turn it into not just one job, but 5 separate jobs underneath one of them. So Slurm is managing it as if it's one job. You can cancel it. You can look at it as if it's one job, but it's underneath the hood, it's 5 separate jobs, each with their own task ID. And this example is just one way to say, since the same program is going to be running on every single machine, running the same thing X number of times is going to give you the same results X number of times, hopefully. So this is one way you can tell it, okay, in that same program, do different things depending on which array ID you happen to be. Again, SCADMD's documentation has better details on things you can do with arrays. This is kind of clunky example of how to use it, but it does indeed work. So if I actually run this one, actually I won't run this one just to show you the output from it. You can see on this one, I basically just ran the program. You can see I now have job ID underscore array ID, so I now have 5 jobs running. In this case, it gave me multiple nodes because I was using an older version of that script. The current version of the script is only 1 node. And then my output files changed a little bit. So instead of being slurm dash job number, it's job number underscore ID array ID. And then each one that's running gets its own output file. So if you're running something to say that, okay, I just need I have this large set of data and my jobs are all serial. Well, if you only have want to run 10 of them or 50 of them, sure, go submit 10 or 50 jobs individually if you want to, no problem. If you have hundreds of jobs or thousands of jobs, you have to use Slurm arrays. Kamiak isn't really built to do high throughput computing. It's not made to just churn through jobs as quickly as it possibly can. So Slurm arrays are kind of the recommended way that Slurm has themselves to make Slurm be able to handle large sets of jobs easily. The next thing I'll show real quick is interactive jobs. IDEV is a little tool that we pilfered from another university for our own use. And this is what you can use for interactive development on Kamiak. So when you run IDEV, it does not support all of the options for Slurm. It only supports a basic subset of them. But what IDEV does is when you run it, it's actually submitting a job for you onto the cluster by default into the Kamiak partition, waiting for that job to find resources and begin running, and then it's going to start a shell inside of your job on a compute node, which it just did right here. So now I'm sitting on CN34 inside of a job, specifically this job. Now I can do my work in here. This is very useful if you're just testing something or trying to figure out how can I work the system, how can I do something with it. It's also very important that if you're compiling something heavy or doing something else that would be pretty heavy on the system, instead of doing that on a login node, hop to an IDEV session and do it inside of IDEV instead. The advantage is that it's interactive. So you have a shell that you can just work with directly. So when you're submitting a job, it just submits the job and then you just wait for the results to come back. When you're in an IDEV session like this, you're still in a job because everything on a compute node still has to be done in a job. But rather than writing a script and figuring out code that way, it's just like you're working on a Linux or Mac machine and you're just giving it commands on what to do. So let's say I've never used Kamiak before, and I'm just like, okay, well, I've never written a script before. How do I write a script? Okay, well, first my script has to module load thing, so I can actually be working off, spelled that wrong. Then I can actually just be working interactively on a compute node, run my other program to see if it works, see what it does, and if it actually does work, then you can take what I've done interactively, kind of just what I've figured out. I can then take that information and write a script out of it, and then now I can just keep submitting those into Slurm over and over again. Now that I know how to do something, how to actually work it in the first place. You don't have to use IDEV. It's just a convenience feature so that if you want to get on a compute node and actually interactively work on something rather than working through writing scripts only, IDEV is how you do that. Yeah, that's the other thing you can do if you want an interactive session. So if you have a job running, right now Kamiak doesn't let you SSH to compute nodes. Like you have to do everything through Slurm. You have to submit a job and get scheduled onto a node. Once you do have a job running on a compute node, you can then SSH to that compute node and look around and see how your job's running if you'd like to. We made that on purpose for debugging purposes mostly. So if you don't want to use IDEV, one thing I've seen at least one other user do lately was to run a job that does nothing but sleep or run screen or something that just sits there and does nothing. So it's a job sitting there doing nothing. But then this user could then SSH into the node and begin working normally as if they were working on their laptop or something like that. Because there was a feature that IDEV did not have that they needed with X11 forwarding, and that was their workaround to make it work, essentially. So he's right, you can actually SSH to nodes as well if you have a job running on them. But if you don't have a job running on them, you just launch up IDEV and go. A note about compilation. This is the way I compile stuff on Kamiak. I literally tell it, give me 20 cores on a compute node, because I can't do that on a login node. So I can take a session that's larger than I can do on a login node, and I compile faster, and I can get my work done quicker by using a compute node instead. At least now that at least while we still have the resources available to do such a thing. These are a few other options you can put inside of your submission scripts. Again, look at the documentation on ScadMD's website or in man SBatch if you're on the cluster right now. You can see all the options it has available to you. A few ones I'll just mention right here are the time option. So like I said, if you do not give it this option, your job gets by default, the maximum time allowed on the partition you submitted to. But like on my little device query program, if it took longer than 5 seconds, I can know something is not right. I need to go look at something. So I could put a time limit on here to say, if it's been X amount of time, just cancel my job, tell me something is wrong, rather than having your job sit there using resources, doing something incorrectly is not going to be useful to you. You can also chain jobs together with dependencies. You can tell I don't want this job to begin until tonight or whatever you want on there. You've also already saw the constraint one that I used on the MPI job. You can also name jobs if you want to. So instead of just looking at SQ and trying to find your username and job IDs, you can put names in there to try and figure out which job was which if you have multiple ones running. There is also an option inside of SBatch where you can have it actually email you either when your job completes or your job fails or all of the above, whatever you want in there. So if you would like the spam, you can get it. So just moving on real quick, so Shenting has enough time for the compiling section. There's some very basic troubleshooting information I've included here, as well as links to both our documentation and SCADMD's. Our documentation is not meant to replace SCADMD. If our documentation doesn't say something or how to do something, well, we didn't invent SCADMD, or if we didn't invent Slurm, go look at what SCADMD is doing. If you still can't figure it out, let us know. We'll help you out to figure it out. We do have support from SCADMD, so if something is not behaving appropriately, we can ask them to correct that for us. A couple of common things that you might see is if you ran a job and it just kind of disappears, like you run a job, it comes up and says, okay, job submitted, and you get a job ID, but you look in SQ and it's not there and you don't see it anywhere. First thing to do is go look at your output files. Well, did you have an error? Did it crash? What happened to it? Well, if your output files don't exist, this is what I was alluding to earlier, then you really can't tell what your job did. It just, poof, it just disappeared. You don't know what happened. The reason usually that Slurm won't create an output file is because it couldn't create one. So for example, in that data Kamiak training location, none of you have access to write into that directory. So if you tried to submit one of those jobs where you're sitting CD'd into that directory, Slurm can't do it because it can't create your output file for you. So we would try to run your job. You'd get job submitted, job ID, but then nothing would happen. It would just crash and say, I can't create my output files. Unfortunately, because it can't create output files, there's nothing you guys have to actually see that's actually happening. This is one reason why either I always put in my job scripts where I want my output files to go inside my home directory, or I CD to my home directory first, so by default it just goes there. And the other major thing here is if you're running any sort of GPU job, if you don't request a GPU with the --gres equals GPU such and such option, then Slurm will not give you a GPU. If you only request one GPU and you try to use two, you only can see one. It won't let you see more than that. So if you see something like no CUDA-capable devices, you didn't request any. Request more. And I mentioned the memory option earlier. There's a mem and mem per CPU, depending on whichever one fits better for you. One little trick with --mem is if you are a very memory-intensive user, if you say --mem equals 0, that means all of the memory of the node. So regardless of how many CPUs you're using, if you actually legitimately need all of the memory, that's one way you can actually take it. I say legitimately need that because if you take all the memory and you're using one CPU, well, we will cancel your jobs. Don't do that. Then finally, just a little note on what it takes to really be a good user inside of Kamiak. It is one system. It's a shared system for all of us. It's not a playground. It's not somewhere to have fun and just do whatever you want. So there's certain rules you kind of have to follow to be a good citizen in it. Part of that would just be, don't try to do real heavy things with Scratch or data if you can. Use slash data or slash home, but instead use Scratch or local for heavy workloads when you can. Even though it is all going off the same NetApp device, but different set of disks behind there, so it's better to use Scratch when you possibly can. Same thing with the amount of resources you're asking for on a node. It's easier for Slurm to find 10 cores than it is 20, so maybe it's easier to run your jobs if you use less resources but larger jobs. But if you can take an entire node, if your software can do that, especially if you're not using Kamiak partition, you have your own partition, then yeah, it's best to actually use the entire node if you can. That way you're not, if somebody has to use the entire node themselves, doesn't have to wait for half of your job to finish before they can take the other half of the node. And then at the bottom here, I mentioned before, don't compile or do anything super intensive on login nodes. Do not abuse the scheduler. That's a pretty common thing in a lot of locations, a lot of HPC shops. Is people will figure out how they can get every possible second on the machine, and if it's idle, yeah, go for it. But again, it's a shared machine. Everybody has to work together on it. And finally, and as with all WSU policies, don't give out your password to anyone. If you ever have anyone who needs access to your data, they want access to Kamiak, they're on a different university, they're in a different planet, I don't care. Talk to us, we will create them an account, we will give them access to Kamiak. Do not share your password. Okay? And Shenting, I believe you're up.
So the reason we are doing this software installation training is because since we have a lot of people using Kamiak, we're going to have more and more people using. We constantly get requests for installing new softwares, and so we have a variety of people requesting a variety of softwares or different. So when the previous software person left, he mentioned his policy was if only one person requests a software, he wants a person to install the software in his home directory by himself. And if the software is very popular, a lot of people want to use it, and we install it on the system. And also, since we have some backlog at the moment, it'd be nice if you're really impatient and you really want to get your project going, you'll be able to install your software yourself. So we will go through some basic process of installing the software on Kamiak, so you have a basic idea what process to go to and to raise a document, and you'll be able to install reasonably moderate software. So the first thing I want you, the old thing, as I said, the line starts with the $sign, except the $sign itself as the command you can use. So you can type in the command. The first line is wget. That's a common command you use to download from web software package or compressed package. This second line is a continuation of this first line. So just type in the whole thing, and you will see some activities.
Yep. So here you can see using the wget command to go on externally, pull back out this libxc tar file. There we go. So now it's downloading it onto your home directory. I'm going to stay logged in as you if that's okay. Okay. So now you've got it. Now you're going to untar it because this is a tarred and gzipped file.
Right.
So now it's unpackaging all of that. And if you type ls, you'll see, oops, where is this?
Go back to the slide.
Yeah, there we go. Oh, you got a CD into
it. Yes, CD
it creates a directory called libxc. Go into that, and here's all the unpackaged files.
See that I have those highlighted, readme and install, those two files. So we can do a more readme. Yeah, basically, what I want to emphasize is that with every package, usually come with either readme in capital letters, or install in capital letters, or install dot something in capital letters. So either come with both or come with one of them. So it's important you read these files first before you do any attempt to install your software package. And those files usually give you the instruction how to install that particular software, and it is current, it's specific for that package. So it's a good thing to read that. And secondly, it tells you what dependencies. For example, if you install NetCDF, and it may depend on the HDF5 or depend on the pack or some other things. So it tells you all the things what it needs. So you need to read this file to find out what dependencies is needed. You have to have those dependencies on your system. And some of the dependencies are on the system, so you don't have to install it itself. And you can use a where is as the name of the library, for example, or use locate. You're familiar with Linux. So the most important, first important thing is to read those two files. If you see those files, is definitely one of these files is definitely going to be there. And so first thing you need to read those files. Okay.
And so in the install file here, it can tell you, I've got highlighted here, it's telling you the exact steps you need to go through, which are the steps that are then highlighted basically here. Now I'm going to go through, when we do this compilation, normally you would open up, like we talked about, an IDEV session and request a certain number of processors, which is exactly what this one is doing right here. So IDEV C4, that's asking for 4 processors within an IDEV session for you to run your compilation off of. When we tried to do this before with everyone running off of 4 processors, it really bogged down the system. So I'm going to do it right now.
You can request more requests.
You can request more, but we probably don't want to.
You can put in 20 since you were just
So
doing.
I'm going to do it here over interactively, and I'm on this lower part of the screen here. So I'm going to do IDEV-C20. Is that the right format?
Yeah.
Yes. Oh, and a dash. I don't have to have the time command, do I?
We're not going to specify that.
Yeah, I don't think it's a big deal.
You know, if your compilation is not going to complete within an hour, then I'll just give it the dash time. But
Yeah, so it has a 60-minute default. So it created my 60-minute default IDEV session within Jeff's account, because I'm on his account. And now we're going to go through and the process basically that was outlined in that install file. And the first one was a configure one. Where I'm going to type present working directory, and I'm already in the same directory that I started in on. So I didn't realize it would do that. That's kind of handy.
You do the dash configure help.
And so one of the first things that is useful actually is to see all of the configure file basically in this particular case. So some software comes with its own what's called a make file, and that make file has all of the list of all the library locations and flags associated with the compilation. Some software does not come with a make file, and it actually uses instead a little software program called a configure program that creates a make file for you. And it looks at all of the things that are available on the system as you do the compilation, and it makes a make file. And so in this case, it's going to make a make file for us using the configure flag. And there's a series of options that you can use using configure help. And so I'm going to type configure-help. So if I scroll through this configure help, you can see that there's quite a large number of options that I can use within the configure as I'm making the make file, telling it where specific libraries are.
Can you scroll up?
All the way up?
Yeah.
There we go.
This line. So the prefix, dash prefix is a very important option. Let's give you an option where locally, if you don't specify the destination directory, usually by default, it will install your software to user/user/local, for which, unless you're a super user, you don't have a written permission. And so your installation will fail. So by using this dash prefix equal to some directory name you gave it, You can use make directory or directory name. You can make a directory in your home directory. And
That's an example.
in this equal capital prefix, you need to give it absolute directory.
Absolute path.
Absolute path. Right, right. So usually for user will be /home / your username and / whatever directory name you just created. So that's for that.
So we're going to do that here. So now we're going to go through. I'm going to make a directory called libxc install, and we're going to use the configure script that they've written and given us with this code and tell it to put the compiled code into that path. So I just made this directory in a directory above by using .. Now I'm going to look up and see if it's there, which it is. And there's nothing in it now. So now I'm going to run the configure, and I need to put in the username here because that was generic. So it's jeff.white. So now I'm configuring, I'm telling it where it should go, and then I've got some other flags associated with this compilation to tell it to use the Intel C compiler, and the FC is a Fortran flag. Oh, here. There we go. So now this is the compilation process. So it's going through and checking for different compiler options.
So if you're just going to compile, you can put the source code in a Scratch directory, hop into IDEV, do your work there,
and then move it
install
over.
in home directory, for example.
Yeah.
Scratch is faster than what home is.
So it's going to take a few minutes probably for it to do this because it's doing a whole bunch of checks. So let's move back over to the slides and talk about what the next steps are going to be.
Yeah.
So this is just the configuration as it looks through all the system variables that it's going to create and put into the make file. And then after that is when you compile, right?
Yeah, next step, make -J4. That's the compilation step. The number 4 is the number of the cores you want to use for the compilation. You can choose whatever number you want to put. Usually maximum number is 20 because our system has most of the our node has have 20 cores.
Yeah, so it's done doing the configuration, and actually, before I do this, so you can see now it's made a make file, and in that make file is all of the configuration options that it went through. Yeah, so it just made this. You can see that it made it at 1446. And if I look at this make file, it is possible, and I think it's important that you notice that sometimes these make files need editing. So the configuration, just in my own personal experience, sometimes configure doesn't always pull all the options that you want. And so it's worthwhile to take a look at it and make sure that the paths are correct and it's using what you want it to use. And so you can see as we scroll down here, there'll be a bunch of options. Well, sometimes there are a bunch of flags in the front end. This one does not. This one has a little bit, maybe, of package including things. But I always recommend taking a look at the make file to make sure that it did it correctly. And now we can actually type make-j
In general,
20.
You shouldn't make any change to make file unless you know what you're doing.
Yeah.
Because if you mess up with the make file, you don't know what it's going to do. So some of the make files has 1,000 or 10,000 lines long.
Oh yeah, they can be very complicated.
Yeah. So it can.
But if you make a mistake, you can always recreate a new one with the configure, which is good. And so that's while it's compiling, you can see that. So it's compiling right now because I just did make-j20.
Can flip up.
So here you go. You can see that it's doing the compilation.
Yeah.
And then if we go back to this slide, now why don't you go through some of the other commands real fast as it does its compile.
Make check because the is after you do the compilation, you usually want to do a make check to check your compilation is correct. And if your compilation is correct, it will tell you it's passed all the tests, and there's number of errors equal to 0, number of fail equal to 0, a few other things. So basically, you should pass all the tests. And then after you checked that there's no error in the compilation, you just type make install. That will install your package into that directory. You put in the -- prefix. And usually this package you installed will include binary executable, include directory that contain all the header file, and lib directory or lib64 in some case, and sometimes create a man page which contains a document, and sometimes has a share directory that's for some other things.
Okay, so I just got done compiling. I'm doing a make check where it enters. Typically, these guys all have test directories where it'll run those test directories as a consequence of that. So you can see that there's test suites that it has in there, and it's going through all of those. And those might take, and so there were no errors associated with this. You can see this fail, skipping, everything passed. And then now we can do the make install.
Make install.
And then typically during compilation, it'll create a bunch of temporary files, and sometimes those temporary files are removed and some of them are not, which is why now you can go through and do make clean to remove those temporary files. And if you want to really just, like say you make a mistake and you do a bad job editing your make file and you wanted to start from scratch, you do make dist clean and it would remove anything that you created and only leave those original files. So I think the other thing that's important about this is this end part, right?
We need to look at the file we installed. Yeah, just type in this.
So I'll do a list on it, libxc.
Install.
Yeah. And so now you can see it has a bin, an include, and a library file.
Yeah. Type in the start here.
Okay. So this will show you then all the contents of those subdirectories.
So you see that. Now remember we had a option called a share something in the configuration part. So
enable shared.
Enable shared. So let's go back to the screen terminals. Mm-hmm. So if you didn't have that enable shared, you will only create those .a file.
Oh, I see.
Those files are used in the compilation step. When compiler doing the compilation, it will include those files. And those .so files, and that will be linked when you actually run your job. So it's not part of the compilation. So those are so-called the dynamic libraries. And those .a as a static light.
So then the only other thing is if, in fact, when you're done installing, if you want this library to be accessible every single time you log in, then you would put these variables inside your bash profile. So now I just want to kind of conclude with talking a little bit about becoming an investor and the types of services that are available through Circ and Kamiak, and then also a couple closing comments about ways in which you can participate in Kamiak governance and helping it to be a better facility. So first off, we all know, you guys, that everyone at WSU has access to this backfill queue and this 10 gigabytes of storage and any storage that their unit, their colleges happen petition and give to them. However, if you need more, then by all means, please consider or advocate to your advisors, if your students or postdocs, becoming an investor. And basically, there's two different types of nodes that you can purchase within Kamiak. The first are called standard compute nodes, and there are a couple different versions that just vary on the amount of RAM memory that they have available to them. You'll notice that this is a cost, and this is a cost for 5 years for a node. And so it's roughly $7,800 for a 120 gigabyte dual Intel node. And that the 5-year limitation comes about because that's basically the limit of all of the warranties associated with the hardware of those nodes. And after 5 years, typically, people want to upgrade their architecture anyway. There are also special compute nodes that involve the Xeon Phi coprocessors, as well as, no, I take that back. These are the GPU CUDAs, and this is a quad Intel one. And so you can also purchase these extra special nodes if, for example, you want to be able to leverage GPUs on a regular basis, and you have software that can really take advantage of that. Or the large memory as well, you're right. In the context of storage for hard disk space, we have the service center where you can purchase out of our NetApp shelf storage increments on a yearly basis. And actually, the purchase really isn't the right word. It's more like that you're loaned them on a yearly basis. And they're sold in 100 gigabyte or 500 gigabyte units. So 100 gigabyte units are $12 a year, 500 gigabyte units are $56 a year, and you're just billed on an annual basis. So if you're interested in doing that, all you have to do is send a request through the service desk. Hey, I want a quote for this type of node or this amount of storage, and then we'll work with you. Tim works heavily with faculty members in purchases associated with their groups. So kind of some concluding remarks. We'll be sending out a survey to kind of get your feedback about the aspects of this particular training session, since that's our first one. The aspects of it that were useful to you and not useful to you. So by all means, give us lots of feedback. You know, give us more information on basic Linux commands, or skip that whole section, or whatever is useful. We're also in that survey going to be information about what you would feel would be useful for an advanced training session at the end of the semester. So if you feel that a really good training session on scripting would be good, or parallelization, or something like this, let us know so that we can kind of use your feedback to help guide what that advanced training session would be. Other ways to learn more and kind of participate in Kamiak governments, you know, if you're a really active user, you see things that you think would be helpful with respect to kind of a user experience. And I'm not just talking about like software that's available, but more basic things, you know what I mean? Maybe with respect to the performance of the backfill queue or something like this. By all means, please share your thoughts and ideas with our Kamiak executive user group. There's supposed to be a committee that represents all of the users and help to form policies associated with the ones that we're enacting on the cluster. And so those members are Scott Anand Kalya-Ramanan, whose name was really long this morning and I couldn't type it all out, Stephen Ficklin, Thomas Badman. We've got a student rep. He's a graduate student rep. Are there any questions? Are you guys good? Okay, awesome. Thank you. Have a great day.